Good morning, good afternoon, or good evening, depending on your time zone. Welcome to the MIT Joint Program webinar on multi-sector dynamics, or MSD. On behalf of the Joint Program, we are thrilled that you were able to join us today. We hope to have an exciting discussion with you over the next 2 hours. Before we start, we have a couple of housekeeping items. First, please mute your microphone. Recording will be on, but during the presentations only. The questions and answers section will take place after the presentations. Please use the Q&A feature located at the bottom of your screen, and please feel free to enter text at any time. The presentation slides will be shared upon request. Let's now review the agenda. We will start with an introduction delivered by the director of the Joint Program, Professor Ron Prim. It will be followed by 6 presentations provided by our Joint Program researchers, including a project overview and a description of the Triage platform, and presentations on MSD and water, land, economics and energy, health, and infrastructure. We will finalize with a Q&A. Okay. Now, I would like to introduce the director of the Joint Program, Professor Ron Prim. Ron, the screen is yours.
Thank you. Can everyone see me?
Yes.
Okay. I cannot see my image, Horacio.
But I can see you.
You can see me, okay.
Yeah.
All right. So I want to welcome everyone to the Joint Program's webinar on multi-sector dynamics. The MIT Joint Program on the Science and Policy of Global Change was founded 30 years ago to bring together experts in the natural and social sciences to address complex challenges in global change. The overall goal was and is to provide a scientific basis for decision-making in the private and public sectors through innovative multidisciplinary research and effective communication with these sectors. Our approach is quantitative and probabilistic and is exemplified by our unique Integrated Global System Model, or IGSM, framework, embracing interacting environmental and economic components at global, national, and regional scales. The IGSM has evolved over the years to incorporate new phenomena as we learn that subsystems that we used to study in isolation must instead be studied together. Probabilistic projections using the IGSM provide the means to expose risk and then to propose adaptation and mitigation actions that both lower the risks and are affordable, equitable among poor and rich countries, and sustainable. With that short preface, I hand you over to Dr. Adam Schlosser, Deputy Director of the Joint Program, to provide an overview of multi-sector dynamics.
Thank you, Ron, and thank you, Horacio, for your introductory remarks. And thank you to all of the attendees for your time today and your attention. And I hope what we provide you today will be good fuel for discussion and Q&A that will follow. So my job today is to give everybody an introduction to what exactly is multi-sector dynamics. What do we mean by that? This is not an expression or a phrase that is self-evident to everyone. So really what I think we want to achieve here at the beginning is to get everybody on sort of the same page intellectually. And what I'd like to do is to provide a few slides on that and to give you a few primers on the speakers that will follow in terms of the topical areas that we'll get into to dive into, and how this all relates to, again, this broader theme of multi-sector dynamics. So to start, what is multi-sector dynamics and why do we care? Well, we know a lot of things are changing on the planet, as evidenced and documented by the most recent IPCC Sixth Assessment Report. We know that climate is changing. We also know that climate change is not only from natural causes, but now more than ever, what we do as a human species, as a population, has considerable effects and impacts on the environment, not just natural environments, but also the environments that we build and we manage. With that, we also have to recognize that not only are we affecting climate, but our society is growing. It's becoming more and more complex. We have growing population. The resources that we require to sustain that population are becoming bigger and bigger. They're becoming interconnected in ways that we have not seen in the history of human population. So in all of that, in the view of all of that, we must view all of our assessments and predictions now more than ever as a growing, complex, interconnected, interwoven network of resource systems that not just evolve by themselves, but co-evolve and have become increasingly interconnected. It's these interconnections, it's these coevolutions that can lead to risks that we've never seen before, or that we could not anticipate with siloed investigations and siloed predictions. We need to think about all this in a much more interconnected way. And that's really at the crux of multi-sector dynamics. When you hear the word multi-sector dynamics, you really need to think about interactions, coevolution, interdependencies among natural systems, human systems, how these systems are co-evolving, adapting, responding to other systems that in and of themselves are changing, but can cause changes in other systems. We need to do all of that in a way that not only brings together data of across the historical period, but also how do we take that knowledge from history, from observations, and put them into modeling tools, into foresight tools that sharpen our understanding, that sharpen our ability to make predictions. Much to Ron's point, how do we use these tools to quantify risks and of co-evolving risks amongst all these different systems? And how do we begin to exercise our tools in sharpened ways that give us real insights to strategies that not only avoid risk, but also prepare ourselves for unavoidable risks? That is really what is the embodiment of multi-sector dynamics. Next slide, please. So with all of that, there are some considerations here conceptually that, again, to put us all in sort of the same intellectual page that we'd like to bring to bear here. In view of multi-sector dynamics, and again, its interconnected, co-evolving, interdependent nature, there is this conceptual there's a conceptual issue of, okay, where do we begin? How do we think about this system of systems from a starting point and begin to train our assessment tools and our modeling tools and our foresights to giving us answers? Well, in the context of our program, we have viewed this at the top level as a situation of trying to identify primary stressors and receptors in the system. Primary stressors are probably phenomena that you can think of, that you've seen highlighted in many things that we see in the media and covered in many of, again, these IPCC assessments that we've seen recently. One is climate and weather. Again, we know climate and weather are changing. We know that there are events in these systems that can cause damage and harm and threaten our environments, not just natural, but our managed environments and our built environments that we live in. There are economic shocks. We only need to think about the recent pandemic and how it's affected the global economy and supply chains. And to Ron's point, is his opening remarks, there are demographic stressors, growth in population, changing poverty, changes in poverty, changes in the population that's infirmed or an aging population. All of these are putting stresses on all of these different sectors of the multi-sector environment. In thinking about all these stressors, then you have to start thinking about, well, what is receiving these risks? And this is where a lot of the resources that we've talked about already or in our introductory remarks come to bear. And you're going to hear a lot about these in the talks that follow and in the topical areas that follow. A lot of what we're looking at in terms of multi-sector dynamics, both individually and interconnectedly, is our natural resources. We need land, we need water, we need clean air, we need reliable energy, we need productive ecosystems to sustain our population. All of these are receptors to these stressors, and all of these resources are interconnected. One only needs to look at a graphical map overlay of land, water, energy, air, and poverty across the United States, which you see in the center there, to see that there is a lot of overlay and a lot of overlaps in these systems. And again, we will go into a little more details in the discussions that follow. But again, as just an overview of all of these risks, we are beginning to develop tools to do that. In the end, what we really want to get at is, can we begin to identify what, where, when, and how all of these interact, and under what situations do they amplify? Next slide, please. So again, we've talked a lot about interactions. The important aspects of interactions, again, in the context of our particular program and multi-sector dynamics in general, is we have to recognize that these interactions occur from global to down to local scales. And while the tools that we have assembled now are beginning to identify some of the more salient features of these interactions, we also have to recognize that these interactions can occur in very complex, or what we'd like to call nonlinear fashions. These nonlinearities, can we go back? Thank you. These nonlinearities can create what we call tipping points. Tipping points really are events which put us from one point of equilibrium into another state that is either not sustainable, is an instability, or we cannot recover from. The challenge here is how we are able to identify and understand those tipping points. And more so, how do we understand those tipping points in a multi-sector dynamic framework? What do I mean by that? Well, let's just take one of the aspects of our stressors, primary stressors that I mentioned in the previous slide. Let's just think about climate. The map on the left is giving you a depiction of a number of climate tipping points that the science has begun to recognize and begun to study. What the graphic shows is that even amongst those tipping points that we feel pretty confident are very real and very probable or risky, for many of those, for a number of those, there's still a lot more research that's required to really begin to understand and particularly be able to predict or provide foresight as to when and where and how severe those tipping points will be. We need to do that not just for climate, but we need to do that for all of the components of multi-sector dynamics. So the real question is not just where are these tipping points in each of the sectors that we're dealing with, but how do these tipping points manifest themselves across all the sectors and how do they interact? Next slide, please. So how are we going to begin to do this? One of the tools that we've developed under this multi-sector dynamic program is what we call a risk triage-based platform. And what you're seeing here, if you could just click it, Horacio, there should be a movie that goes along with this. Thank you. What you're seeing here is an example of this triage platform. It is a publicly available platform now. We've released version 1 of this platform. The URL is below, mst.mit.edu. We encourage and welcome everybody to visit this site. A lot of the content you'll see in the presentations that follow use this website. I just want to speak to everyone that's listed on this slide. It's been a real pleasure working with everyone. It's rare that you have a team of researchers that really believe in something, and I feel as though we put together the kernel of what will become I think a very impactful tool, again, in building not just the assessments of what we think is happening now, but also how we can use our prediction tools to provide foresight into these instabilities, to these tipping points that come across all of the components of the multi-sectoral dynamics scope. Next slide, please. So to give you some examples of what this platform does, essentially what the platform is doing is to try to bring together various metrics of risk and impact across all the sectors that I've mentioned, all the receptor sectors that I've mentioned, and to build a quantitative approach to combining these risk metrics so that you can not only look at risks individually, but begin to ask questions about what if I overlaid various risks across these sectors, how might they amplify, how might they co-evolve, and how, do they even coexist presently in our system? So one example is if you were just concerned about flood risk and the ability of people to cope with that flood. Our tool provides the ability to look at flood risks. The shades of red that you see are the areas of higher flood risk, as well as poverty. And you can look at these two individually, or you can ask the question, well, what if I combine the two risks? What does the resulting landscape look like? And just by doing this very simple procedure on our platform, which took me about 5 minutes to do, you get the map, which you see below in the lower left. And what's probably the most salient aspect of that resulting landscape is you begin to see very clearly that when just combining poverty and flood risk, there is a very clear hotspot region that flank the lower Mississippi River Basin. And it brings to bear a lot of interesting issues. One is that the Mississippi River is a rather large basin. In areas of the upper Mississippi River Basin also have flood risks. They may make decisions about how to avoid that flood risk, which typically involves building higher riverbanks, levees, and just channeling all of that flood, all of the high flow, river flow downstream. Well, that may not be a very good solution when you think about the resulting risks that would occur in the lower Mississippi River Basin, and the fact that many people there are not really well prepared or have the resources to confront that heightened risk. So there may be a bigger, larger, more equitable solution to flood risk in the upper Mississippi River Basin that needs to take into account more detailed modeling analysis. And that is really at the crux of this triage-based approach. It is a screening level application, a screening level visualization tool that allows you to look at risks, identify hotspots when combining risks, and making decisions about how to deploy perhaps more detailed, more in-depth analysis to solve a more complex problem at a higher granularity and scale. Next slide. Another feature of this tool that we are actively pursuing is to also verify this tool and to make extrapolations into other areas. This is an example to sort of highlight that feature, which is basically showing you a combination on the left of water quality risk and other environmental equity issues such as race, poverty level, and unemployment. And when you look at that resulting map, you see on the left, we've compared this map with a point-wise assessment provided by the Environmental Justice Atlas. And what we find is that the hotspots that we identify from this map correspond to documented cases of severe environmental injustice, particularly relating to water quality issues. Many of the counties that you see in California, in Central Valley in California, along parts of eastern and southern Texas, as well as the Genesee County in Michigan, which is where the very well-documented and highly profiled severe water quality issue in Flint, Michigan occurred. You see a lot of this very consistent mapping with our tool. When thinking about that and recognizing that it looks like our tool is conveying again a risk across different sectors that's consistent with what's happened, what it also conveys is that these are not isolated risk-prone areas. Looking at the contiguous U.S. on the whole, you see that there are many other counties across the U.S. that are equally preconditioned to these types of risks. And again, this is another feature of this tool that we are actively developing and pursuing. And it not only brings to bear risks that occur now, but it also raises an awareness of, well, if these are areas that are already preconditioned for severe water quality injustices, what does the future bring? Next slide. And with that, one of the active areas of this triage platform that we are currently endeavoring is to not only combine all of the data that you've seen in these introductory examples, but how do we then bring all of that together with our projections? As Ron mentioned in his introductory remarks, over the past 3 decades, the joint program has been a leader in the area of integrated assessment and risk projections, risk-based projections. And the real opportunity here now is to take all of the scenarios that our team has worked on over the decades and apply all of those projections to this risk triage platform to give us projections of the future, where risks evolve, and then how can we put our more detailed tools, when we see those hotspots, how can we apply our more detailed tools to look at adaptive strategies and their cost effectiveness. Next slide. So again, before we go into the topical presentations, topic areas of presentations from my colleagues, a few takeaway messages. You're going to be hearing a lot about now different sectors of the MSD space. We're going to be talking about energy, land, water systems, infrastructure, energy economics, health, climate, weather extremes. And really what it comes down to is that the strength here, or really what's going to be one of our biggest challenges or opportunities, is how we link all of these together. The triage platform is what we feel is an important kernel in all of this. But as you will see in the presentations that follow, we need to begin to put all of our models to task to not only assess the individual risks in the sectors, but how we are going to put together these in a linked fashion, step all of these models forward to look at, again, important interactions, tipping points, and to provide foresight that supports informative action towards obviously a sustainable, resilient, and prosperous world. So with that, thank you all. And I will pass it on to Horacio, who will introduce our next speaker.
Thank you, Adam. Our next speaker is Dr. Jian Gao, a research scientist at the Joint Program, and Jian will talk about MSD and water. And all speakers will be also sharing a few words about their background and role in the MSD project. Jian, the floor is yours.
Okay, thank you. So, yeah, my name is Jian Gao. I'm a principal research scientist at Joint Program. My research focuses on understanding the role of the land in shaping the weather, climate, hydrology, and also biogeochemistry on local to global scale, using various tools, including model simulation, like observation, satellite data, and also machine learning. So in particular, I'm interested in the hydrological cycle and their shifts to the climate change, including extreme events and also risk-based water resource assessment. So today I will talk about a high-resolution water quality model over the United States. So why we should care about the water quality? So intuitively, we know that water quality is closely connected connected with our daily life. So poor water quality can really complicate the drinking water treatment and the distribution systems. It can also affect water supplies, which directly affects human health and welfare. So these physical impacts can have substantial economic impacts as well. So, for example, it can force the poor water quality can force the restrictions on a number of the recreation and the commercial activities. So including like lake and river visits, boating, swimming, and a number of like other activities like fishing. So, so many studies have found that like changes in water clarity can directly lead to the property value changes in the surrounding communities. So this is why we really cares about water quality issues. So water quality is a very typical example of the MSD topic by interacting with many earth system components and also socioeconomic elements. So first, climate can have very large impact on water quality through the air and water temperature, precipitation, runoff, and extreme events. Agriculture can also interact with water quality by application of the fertilizers. So water quality can also be affected by human wastewater treatment and municipal or industrial facility level pollutants. Next slide, please. So I would like to provide some background information about how water quality issue is formed and which can help better understand how we should model water quality. So water has some very unique properties. It's a very excellent solvent for many gases, minerals, and organic compounds. So water also has very unique temperature density relationships, which can directly lead to the stratification of lakes, particularly in the summer. So on the bottom, we show that here it shows a typical vertical structure of a lake in the summer. So it generally consists of like 3 layers. On the top layer is warm, light, and well-mixed zone, then followed by a transition zone with rapidly change temperature. This layer is very resistant to wind mixing, and it serves as a barrier between the first layer and the third layer. Then the third layer is really relatively cold and heavy, and very dark and relatively undisturbed zone. So this lake stratification can lead to very different distribution in terms of concentration of dissolved oxygen, phosphorus, nitrogen, metals, and other compounds compared to the well-mixed lake. So all this distribution can directly affect the algae population, water supply quality, and fishery management. Next slide, please. So this slide, I just want to compare the spatial scale of the different river basin settings used in different studies. So on the very top right, it shows the typical 18 basins, two-digit HUC designated by U.S. Water Resource Council. On the top left is the water resource global version models we have been using in our outlook. This is the 14 basins. Then on the bottom, it shows the over 2,000 basins over US. It's based on the 8-digit HUC developed by USGS. So this high resolution model really can provide us very detailed spatial structures compared to other two versions. Next slide, please. So I would like to give a quick overview of the model structures for this water quality model. It consists of a series of the linked models. So climate is at the top of the modeling chains. It can be historical and from observation, or for the future. We can also use future climate from GCM. So the typical variables including for input, including precipitation, temperature, wind, radiation, specific humidity, and pressure. Some is on monthly interval, some requires daily input. So this climate, we use this climate to first drive either hydrological model or land surface model to simulate the monthly runoff. Then climate also combined with the soil and crop characterizations, and also population projections to drive the water demand model. So this water demand model will give estimate of the water requirements of the municipal and industrial, as well as the agriculture sectors. So with this runoff and demands, they both input to the water supply, water resource system model. This water resource system model will produce a time series of the reservoir storage, release, and allocation to various demands to the system, which also include the municipal, industrial, agriculture, and environmental flow, transboundary flow, and even hydropower, etc. So in this model, it will involve the optimization between the different sectors for the demands. So the next this managed flow and the reservoir states. Oh, what's going on? Reservoir states will together with the loadings to input to the water quality model on the daily time step to simulate a number of the water quality constituents in the river and reservoirs. But finally, the concentration of this water quality, this simulated water quality constituents are passed through to a valuation model to estimate the costs or benefits associated with the economical cost or benefits associated with the water quality changes. So for the water quality and measures, we consider several metrics, including water temperature, dissolved oxygen, organic carbon, nitrates, including 3 times, ammonia, nitrogen, and organic, then phosphate, organic, and inorganic. And we also have the proctan and metals and salts. So for valuation, we use the terms called the willingness to pay as a metrics to evaluate the economic impacts. Next slide, please. So our model, our water quality model count for both point and non-point loadings. So the point source mainly comes from the municipal industrial wastewater water treatment. Non-point source come from major 2 sources. One is the agriculture, nitrogen, and the phosphorus from fertilizer, and another is the human waste. So on the left, we show the average, the spatial distribution of the average seasonal nitrogen loadings in kilogram across the United States for different basins. So we can see that there are quite large seasonal variations for this nitrogen. Okay, so there's some like animation going on. So we see a large like variations in this nitrogen loadings. We see that usually in the from spring to the summer, it's characterized by the relatively high loadings. Then in the winter, it's generally characterized by the low loadings. this is expected as the agriculture activities are more intense during the spring to summer. And but in the fall, we also see the Midwest still it also shows quite high loadings. And in California, we see almost the relatively high loadings across the entire year. I think this is associated with how intense the agriculture activity it is. Next slide, please. So for the water quality variation, we use this valuation system developed by the VAN in 2007. So the diagram shows the basic procedure. So first, for each simulated water quality constitutes, we apply this their concentration to a curve which scale the value between 0 to 100, use the transformation function. So then we apply this constituent specific weight to calculate the weighted water quality index. Then we can compare this water quality index between different scenarios, or even compare to the historical conditions to understand the changes in water quality index. By multiply these changes with the watershed population, we can estimate willingness to pay as a valuation matrix to estimate the associated economic impacts associated with the water quality change. Next slide, please. So moving forward, so in pretty soon we are going to start the future projection and various policy scenarios. This can allow us to estimate the social economic costs or benefits associated with the water quality, like what kind of mitigation benefits we can get. Those kind of questions we can answer. Then we also interested in running the large ensembles of this water quality model to account for various source uncertainties in water quality, either from regional climate or different socioeconomic parameters applied in our IGSM models. So application of these water quality models can allow us to identify like a very high resolution risk hotspots associated with water quality. It can also be integrated into the Triage platform to assess compounding risk stressors. Yeah, that's all my talk. Thank you.
Thanks, John, for your great presentation. Our next speaker is our Angelo Garcial, who will speak about MSD and land. Angelo, please go ahead.
Hello, everyone. Can you hear me, Horacio? Can you see me?
Yeah, we see you and we hear you.
Okay, thank you. Hello, everyone. My name is Angelo Garcial. I am a research scientist at the MIT Joint Program, and I have been developing socioeconomic models able to represent environmental resource and the use of those resources, as also as models that can interact with terrestrial ecosystem and environmental models. I have investigated here at the Joint Program aspects related to land use change, agriculture, deforestation, bioenergy, nature-based solutions, environmental and agriculture policies, and similar topics. Well, I would like to share with you today some of our developments on representing and investigating the role of land in this multi-system dynamic framework. The importance of representing land use and land use change in this framework is quite evident, since land is the most or among the most relevant natural resources for agriculture and food production, as also as natural ecosystems, forest, biodiversity, water cycle, water quality, carbon storage, and many other environmental services all depend on land conservation and land management. Many interactions and relationships among the human systems and the natural systems have land as a central component or a relevant part of this interaction of systems. So multiple scale economic environmental pressures can lead to compounding impacts on land and bring instabilities to the human or to the nature systems, or can increase the risks of damage to agriculture or to the environment, or those interactions may depend on the resilience of processes related to land. So next slide, please. To investigate all those interactions where land is a central component, please we built and apply several tools to investigate those connections and interactions. It's also to build risk metrics. And to do so, we need a lot of data. We collect and process data from several databases. In the case of the US, most of our land use source come from the USDA, but also from EPA, Environmental Protection Agency, and the economic information is usually provided mostly by input-output tables and systems like BMDC and InPlan. All those databases are used to build two main tools or two main models under this multi-system dynamic approach. We have a global model representing 18 regions of the world, and also we have a model representing more than 30 states and group of states inside the US. Next, please. Of course, there are several challenges when we are trying to do this kind of modeling effort, as the complexity and uncertainties in all the economic and environmental relationships involving land use. Also, the multiple dimensions that we want to represent and address on those models, and the spatial representation and data and computational requirements associated to that spatial representation. Next slide, please. So I would like to share with you guys a recent application that we did with our modeling framework. Please, one more. So we asked this general question about how global forces or global stressors could impact land use in the US in the future. And those stressors would be population and economic growth, agriculture yields, climate impacts, international trade, diets, and so on. And then we would like to understand how increasing pressures or decreasing pressures would pose challenges on carbon storage, pollution, biodiversity, and if those stressors could lead to some tipping point on land use in the US or not. Just to give some idea about what has happened in the US in terms of land use trends in the past 30, 40 years. Just click one time, please, Horacio. We have seen in the past, the recent past, that cropland areas in the US has decreased a bit, pasture and grassland areas have increased, and total forest areas have increased in the continental US. And then we want to see if those trends will be intensified or will be reversed in the future under alternative pressures. Please click one more time. In this slide, I'm just showing that we are looking at this problem first at the global level. So we are shocking our system with global stressors on population, climate change, economic growth. And we want to see what's going to happen in the land use changes in the US. In the future, we want to understand better how those stressors will come up with some spatial change inside the US. But at this moment, we are just looking at the US as an aggregate country. Please, one more. Please, one more click. So just to give some idea what our multi-system dynamic modeling approach does, this scheme shows that we represent environmental resources like natural lands those lands can be transformed to agriculture use. The agriculture sector will produce several primary goods. Those primary goods go to sectors, the industrial sectors that will manufacture final goods, and households or families can choose among the agriculture, the industrial, and many other goods and services that are provided by other sectors besides agriculture, given what they need, what they prefer, and the amount of income they receive. Also, please, one more click. The natural resource in the model, Horacio, can you click once more? The natural resource can produce several environmental services, and those environmental services are also used by the society, by households that can trade off how much they want of these compared to other goods and services coming from the economic sectors. In this way, we close completely the trade-offs and interactions among nature and economic systems. And then we have a setup to apply shocks in these systems in terms of economic change or environmental change. Please, one more click. So in this application, the main results that we found have to do with how the system will behave under higher pressures affecting land use or lower pressures affecting land use. Then we test individual factors or individual stressors like higher population growth or high economic growth, lower economic growth, lower population. And also we test applying all those stressors at the same time. And what we have observed is that under higher pressures, we see an increase in pasture area, increase in the use of fertilizers, chemical use, and intensification of agriculture, and it leads to more pollution, nitrogen emissions, methane, and CO2 emissions. Next slide, please. So our main conclusion at this point is that the current trends that we see for land use change in the US, they will intensify by higher pressures in terms of agriculture production and land use, and they will decrease under lower pressures. But we don't see any evidence of tipping points at this time, since when we apply all the stressors together, the impacts are not much higher than applying one of each stressor alone. However, we should be concerned about fertilizer use, nitrogen, methane, and how much we need to intensify agriculture to cope with those stressors. And then it will pose some challenges in terms of environment to the society. Next steps, we want to refine our spatial results inside the US at the state level, and we want to improve our economic and environmental connections. I think it's all that I had to show. I'm happy to answer any questions at the Q&A part of the webinar. Thank you.
Thank you, Angelo, for the great presentation. We are going to have now our Jennifer Morris speaking about economics and energy. Jennifer, the screen is yours.
All right, great. Thanks. Yeah, so I'm Jen Morris. I'm a research scientist at the MIT Joint Program, and I'm also heavily involved in the MSD community of practice. My research focuses on socioeconomic systems, energy economic modeling, and linking human and Earth system models. I also focus on uncertainty, which is an important component of MSD research, and how to incorporate uncertainty into our models. So today I'm going to give an overview of economics and energy and their role in MSD. So as you might imagine, economics plays an important role in MSD for several reasons. First, economic markets link sectors and systems together. Supply and demand of various sectors for factors of production, such as capital, labor, materials, and energy, drive prices of those factors, which feed back to affect demand and supply. So for example, if the electricity sector stops using coal, the price of coal will drop, which could incentivize the industrial sector to then use more coal. Also, the output of one sector is often the input to another sector. So many sectors and systems are linked through economic markets. Second, economic growth is a key driver of many changes, and it's also highly uncertain. So a wide range of sectors and systems can be affected by both short-term shocks to growth, and of course, we've seen this during the pandemic, the impact of COVID on the economy, and in turn, several systems from transportation to energy, health, construction, as well as long-term trends in economic growth. An example of this would be increasing GDP per capita trends in different countries might lead to higher demand for meat, in turn, higher land use changes to convert land for livestock, and more impact on emissions. Or another example would be higher demand for energy as population and GDP grow, and the corresponding impacts on emissions and climate change. So a third reason why economics is important to MSD is that many objectives or motives are economic based. So for example, the goal might be to minimize costs or maximize profits or make cost-effective investments or improve economic equity and outcomes. And so when we are thinking about interconnected sectors and systems, when we take a broader systems view, that can change what we see as the actions that are needed to achieve these objectives rather than looking at one sector at a time. And then energy, of course, also plays a central role in MSD. Energy is a key component in most sectors, and decisions about energy can impact the overall economy as well as natural systems, for example, through the impact on emissions and climate change or through direct pollution from the burning of energy sources. And the energy water land nexus is a central example of systems that are closely linked and closely co-evolve. And in many ways, research into this nexus is a precursor or subcomponent of MSD research, which really pushes the bounds to include additional systems and sectors and their interactions. So next slide, please. Here we go. So a cornerstone of the joint program has long been our economic projection and policy analysis, or EPA model. And this tool represents all sectors of the economy in all regions of the world at the level of aggregation shown here, with particular attention to energy technology sources across different sectors, such as electricity, transportation, and industry. And the purpose of the model is to project economic activity, energy, and emissions. The model is based in economic theory, and one of its strengths as a tool is its ability to model the interconnections between sectors. And thereby, it can capture important feedbacks and ripple effects through the economy. Next slide, please. And this modeling tool can be linked across systems and scales, which is another main focus of MSD. So we link our human system model with our Earth system models to project future climate change, as well as impacts on water, resources, and quality, land use, air quality, and other impacts. And the end result is, as you've heard mentioned throughout this presentation, is a multi-system, multi-sector modeling framework that really includes representations of economies, energy, water, land, natural resources, technologies, populations, infrastructure, climate, and weather. And we use this modeling framework to explore issues across scales. So our global modeling provides boundary conditions and global drivers for our country and state level modeling, as Angelo had just mentioned. And this then provides information about impacts on local systems, which then can be used in decision-making frameworks at local levels. So next slide, please. And within our risk triage framework, Specifically, we're interested in economic and energy data that can provide insight into various potential risks. So for the economy, we currently represent the data and metrics listed here. So things like GDP, GDP per capita, some employment categories, personal income, etc. The map is showing county level GDP in 2018 as an example. And then next slide. And for energy, we're currently representing the data and metrics listed here. So employment in energy specific categories, such as fossil fuels, renewables, motor vehicles, things related to energy expenditure per capita or as a share of GDP. The maps that I'm showing here are showing employment in fossil fuels and employment in renewables, which largely occur in different places, as you can see. And then the next slide. And so we can use the risk triage platform to combine different metrics to produce various insights about risk. So for one example, we can look at employment in fossil fuels, which suggests potential risk of economic hardship if the country moves away from fossil fuels and toward low carbon alternatives. That might result in massive job loss, for example, in these areas. We can then combine this metric with data on population below the poverty level. And so areas that already have a high poverty rate and also have the potential for significant job loss with a decline in fossil fuel use could be good candidates for targeted job retraining programs or green jobs development. Next slide, please. As another example, we can look at where employment in fossil fuel is highest, which is where the most fossil fuel assets are located, and combine that with information about flood risk to identify fossil assets at risk of flooding. So we can see on the map furthest to the right, some risk hotspots in Pennsylvania, West Virginia. And next slide, please. As a final example, we can look at energy expenditures as a share of GDP and combine that with the population below poverty level to gain insight into energy poverty or the lack of access to affordable energy services. So these are places where people are poor and they need to spend a high share of their income on energy. And again, looking at the map on the right, you see hotspots really in the Gulf Coast, the southern states along the coast there, and additional hotspots in other places. So next slide, please. So far, our, I think you can give it one more click. One graph didn't show up yet. Yeah. So our risk triage platform includes data describing the current state of the country. However, we intend to extend the platform to include future projections. So to that end, with our multi-system, multi-sector modeling framework, we can provide projections for a wide range of outputs, including many related to the economy and energy. For example, we can project GDP at a global, country, and state level under various scenarios or assumptions about future conditions. We can also look at GDP or welfare impacts of different interventions or policies. And of course, future projections are uncertain. And our team also focuses on quantifying that uncertainty, which again is a main component of MSD research and the topic of one of the MSD working groups. And there's potential for this type of uncertainty quantification to be incorporated into the risk triage platform as well. So next slide, please. Similarly, we can project things like sectoral output, sectoral emissions intensity, primary energy use, energy prices, and a plethora of other things. And including quantifying uncertainty around those projections. I'm not going to go into detail here, but just some examples of some of our uncertainty quantification work that also involves projections into the future. So next slide. So to close, mention that our modeling and risk triage frameworks can provide pictures of current and projected future economic and energy landscapes. They can also capture and highlight interactions between different sectors and systems, including compounding risks or risks that occur simultaneously in the same location. As I just mentioned, we're also extending the risk triage platform to include projections. And we're working on adding additional data and metrics related to energy and the economy, some of which I've listed here, things like production and consumption of energy, energy resources, infrastructure, as well as for the economy, things like sectoral output, imports and exports or interstate trade, potentially things like the cost of living, economic complexity, or inequality metrics. One of the challenges that we've faced in particular for energy and economic data is the level of aggregation, the scale of the data is largely at the national or state level. So finding it at the county level has proved challenging. So if anyone on this attending this webinar has any tips for that, we'd greatly appreciate it. But we're pushing ahead in areas where we can and looking at state level when necessary. So with that, I thank you and I look forward to the Q&A session.
Thank you so much, Jennifer. Our next speaker is Sebastian Easton, who will speak about health. Sebastian, the floor is yours.
Thanks, Horacio. So, as was introduced, my name is Sebastian Easton. I'm a research scientist affiliated with the Joint Program at MIT. And my background and the background of my role in this project is that I look into understanding the ways in which air pollution can change at a distance. So that distance can be physical in the sense of something like aircraft cruise emissions effects on air pollution, but it can also mean how climate change interacts with air pollution, or how something like a change in electricity generation because of something like a carbon tax might redistribute damages from air pollution across the country. So if we go to the first slide, the reason that air pollution becomes part of the multi-sectoral dynamics question is in part just because of the scale and the magnitude of the problem. Even in the US, a country with relatively clean air, air pollution is estimated to cause, in a study that we published just recently, up to 100,000 premature mortalities per year, and that's just from combustion emissions. So that means 100,000 more people dying every year than would otherwise be the case if we were able to eliminate those emissions. But it's beyond just the magnitude of it. There's also significant inequity in terms of impacts. The plot on the right, which is from that paper, shows an estimate of the number of deaths per 100,000 population in each state, which are exported. And that means that the pollution produced by that state is producing more impact through air pollution outside of the state than that state is receiving from other states. So it's a sort of crude measure of inequity. But of course, it goes to every scale, right down to the neighborhood and block level. We have inequity in air pollution impacts. And so that means that air pollution is a difficult problem. The causes are both diffuse and specific, and these impacts are highly contextual, and that places it squarely in the domain of multi-sector dynamics. So to understand the impacts of an intervention, we have to understand that context and the context in which that intervention takes place, and the implications of that intervention for the background atmosphere into which that air pollution occurs. Next slide, please. So right now in this project specifically, we started by looking at current day pollution. We seek first to understand where air pollution is occurring right now and how it combines with other risk factors so that we can understand the multi-stressor risk hotspots and start to predict how those hotspots might evolve or change in response to the interventions that are being planned. And the data I'm about to show is actually directly from the tool that we've been discussing, incorporating some of the best estimates that we have of the present day population and their exposure to air quality through estimates of air quality. In the future, we will be extending the tool to look at future climate scenarios. But right now, I'm not going to be talking about that too much, but I'd be happy to discuss that more in the Q&A. And that will be using the IGSM GCHP system that's been discussed so far, as well as the EPA system to understand how changes in policy and changes in economic circumstances might affect air pollution. Next slide, please. So just to give a very brief example of the sort of insight we can gain from this work, I've thrown up an example that was actually very easy to extract from the tool. On the left, we have an estimate of the exposure to air pollution in each county in Texas under current day conditions. And what you can see here, and this is air pollution actually as particulate matter of less than 2.5 microns in diameter. So fine particulate matter in the atmosphere. And this causes cardiovascular disease and cerebrovascular disease, and is the primary driver of those 100,000 mortalities per year I was talking about in the US alone. And what you can see on the left is that essentially the entire Gulf Coast of Texas is a risk area. We have significant exposure to air pollution throughout this region, whereas that air pollution fades away somewhat as we move further and further inland. But on the right, we have the percentage of the population in each county which is considered to be in poverty. And you see a somewhat different distribution, basically throughout the southern border, but in particular towards the southern tip, we see an increasing percentage of people in poverty. And seeing these two together, you immediately get a sense, well, okay, then South Texas is a risk hotspot when it comes to the combination of air quality and poverty, an area where a vulnerable population is being directly exposed to harm. Next slide, please. What's convenient and actually extremely useful about the tool that we've been discussing is how these hotspots pop out immediately. In this case, I've taken the air quality data I was discussing and the poverty data I was discussing, combined it with the water quality data that was discussed earlier directly in that tool. And we can see that this South Texas area really pops out immediately as a risk hotspot for environmental damage to which a vulnerable population is being exposed. Now, this is, as I say, talking about current risk, but we are going to be combining this risk data with climate data, finding areas which might already be hit by population, which are going to experience additional stresses in climate change. But we're also going to be incorporating a more direct understanding of the interactions between climate and air quality, meaning that not only will some populations be hit by climate change directly in terms of things like increasing hurricane likelihood, but they're also going to have that air pollution evolve in response to climate change and with climate change. And this will be a unique form of stressor which we want to evaluate. Next slide, please. So our tool, as I mentioned, already incorporates health data for every county from the CDC. And that means that it's an asset in understanding the likely impact of future interventions, as well as understanding the current impact of air pollution, because we can use that health data to look for areas which might be hit harder by an increase in air pollution, or which might benefit more from a decrease in air pollution, because that health data affects what air pollution does. And we will be using this information to better understand the multi-sector dynamics and consequences associated with climate change, environmental policy, and economic intervention. The thing I really want to point out about health and air pollution is that health impacts from air pollution are essentially a continuous and recurring tragedy. It's a price we pay every year that we don't act to reduce it. So they really need to be included in assessments of the risks and benefits of potential future interventions. Final slide, please. So just to wrap up, right now, we're already able to incorporate our understanding of current day air quality and public health into multi-sector dynamic research. And we're using this data right now to identify and dig into multi-sector risk hotspots, which includes changes air quality as it stands right now. And those multi-stressor hotspots where air quality might yet be a problem, but is definitely compounding other problems. And we're working to extend this to also consider other pollutants. We started with this fine PM2.5, which is, I'd say, almost a classic pollutant at this point, but we're starting to consider, say, ozone, which might occur elsewhere or in ways which is somewhat unrelated to PM2.5, as well as other criteria pollutants like sulfur dioxide and nitrogen oxides. And to that point, we're working to expand our approach so that we can better understand how climate change and policy interventions will affect environmental risk across the country and shortly across the globe. Thank you.
Thanks, Sebastian. Our next speaker is Alyssa Mccleskey. Alyssa will speak about infrastructure. Alyssa, please go ahead.
Hello. As you mentioned, my name is Alyssa Mccleskey. I am coming to you from near Boulder, Colorado today. And my background is actually in water resources engineering with an emphasis in climate change and river basin analysis and a lot of interdisciplinary work there. I am currently a project manager at the National Center for Atmospheric Research, and I teach at the University of Colorado in the Engineering Management Department. And I also have taught GIS, Geographic Information Systems, in our civil engineering department. And that's kind of what brought me to the group here with my expertise in spatial data analysis, being able to bring these large spatial data sets together, being able to manipulate them into the data that we need for our framework. I also have some background in indicator work. That's been helpful in kind of deciding what we want to include in our framework. And also, which brings me today to talk about infrastructure, a few of the really unique aspects of this particular framework that we've added in here compared to past studies, I would say, is having infrastructure as a sector and also being able to combine these metrics that you've heard about so far. So go ahead to the next slide. So if we can kind of step back to the main focus of multi-sector dynamics, it's that interaction and interdependency between the human and natural systems, and then also those interactions between those sectors. So infrastructure is one of those sectors. In addition, it critically links the different systems and sectors. And so we can kind of think of two aspects of infrastructure. One is that near-term multi-sector infrastructure investment that's going to help us to shape our long-term pathways and help guide us what's going to happen into the future. Also, when we're dealing with the infrastructure sector, we have to think across different spatial scales. So down at the city and county level, up to the state, regional, national level, and even international level. And then also across the different sectors, a lot of what we've already discussed in today, infrastructure brings those different sectors together. In terms of the triage framework, having infrastructure included as a sector helps us to prioritize that need for capital investment and kind of focus on those areas where we want to enhance resilience and equity issues. It also helps to alert us to areas where we have risk of cascading failures across different configurations of infrastructure. And then we can also dial down further into information about operating rules, demands, and settlement patterns. So kind of highlight those areas and give us reason to do some future research. Next slide. The next couple slides I'm going to show you are the infrastructure that we include right now in the framework. The background map in the next two slides is just showing population density, so it's not too busy. The dark purple areas is just where we have more significant population. We have highways and major railroads, which is represented by those darker gray lines. The thicker the line is usually the more important or significant of a transportation system there. And then the blue lines we have is representing marine highways. And the thicker the line that's represented there shows us the more products that's being moved or materials that are being moved on that particular waterway. So for example, you can see the Mississippi River is fairly thick. That's one of our largest areas where we transport goods. In addition to just having the locations of those marine highways, we also have information about the tonnage that's being moved or transported in those areas. So we can break down into the tonnage of coal and petro, food, crude materials, chemicals, manufacturing. So we can look at each of those individual subsectors, or we can look at the waterway as a whole as to how much is that waterway is being used. Next slide. Next here, we have representing the energy infrastructure. We use transmission line. We have two different categories of transmission lines. One is a level 2, which represents between 230 to 344 kilovolts. And that is the green line that you see on the map there. And then we have a level 3 category, which is anything that's greater than 345 kilovolts. And that's that darker red lines that you see there. That's basically our energy infrastructure that we have laid out. And those data is provided by the Homeland Infrastructure Foundation level data. And then as a side note, I'm also talking about critical habitat because it's another layer that we've introduced onto our framework. And we define critical habitats as all critical habitat for all species that are either listed as threatened or endangered according to the United States Fish and Wildlife. And that you can kind of see is condensed up in the northwestern area, that the blue lines are represented there. Almost looks like some little rivers. And then down in the southeastern area, you'll see more of the critical habitat located there. Okay, next slide. And now I'm going to just go through a few different examples, kind of show how we can use the infrastructure and critical habitat data. The first example is just a very simple map overlay, allowing us to see where this infrastructure is occurring. The example that I'm showing here, I've zoomed into a county in southern Illinois, and I have a kind of a more detailed case study that I've done on this particular area. But looking specifically at a business that wanted to relocate and kind of using all of these triage metrics to see what might be happening in this area, and infrastructure is one of them. So they wanted to see basically what's their location and robustness to be able to transport their goods. And you can see on the left side there in terms of transportation infrastructure, there's a significant amount of infrastructure in this area, both railroads and highways, and also located nearby to a marine waterway there, the Mississippi River. And then on the right-hand side, I've just zoomed into that area looking at what do we have there in terms of the energy infrastructure or the major transmission lines. So we have one of the higher level transmission lines running through kind of the northwestern area of that county. Okay, next slide. Now the next few examples, I'm getting into combining some of the metrics. The nice thing is that's already been presented by some of the other sectors of how we do that. So I'm looking here at our transmission lines, and I'm thinking of different metrics that might impact our energy infrastructure. So in this particular example, I've combined flooding with temperature stress, thinking some of those climate issues that might impact our energy infrastructure, and then also looking at where we have the highest population densities. So this example immediately highlighted some areas in Oklahoma, Arkansas, Missouri, Tennessee, and North Carolina as particular hotspots where these risks and higher population densities combined create some sort of hotspots, and we might want to look in and investigate those areas more. Next slide. Now looking at critical habitat, I've combined some different metrics that I thought would impact critical habitat. So for example, water stress, water quality, flood risk, land disturbance, and temperature stress. Again, this is the real powerful aspect of this framework, that we're able to combine all these metrics and come up with a combined risk. So in this case, it highlighted a couple areas, one in Georgia and another county area in North Carolina, where we're seeing high risk factors from these metrics, and also where we're located with some critical habitats. So again, areas that we would want to investigate further. At the same time, I'll draw your attention up to Idaho. Up there, you'll see kind of a condensed amount of critical habitat. And when I've combined these particular risk factors, I don't see basically any alarms going off. It has a low risk in terms of these kind of more climate aspects. And then if we can go to the next slide. But something else you might think about when you think about critical habitats is development. And a proxy that we can use for development happening in an area could be employment and construction, which we supplied for data for 2019. And so now if I'm looking at employment and construction as a proxy for development, you'll see that area in Idaho really has a high number of people employed in construction, which implies to me that there might be a lot of development going on in that area. And there's a real significant amount of critical habitat. So this sends an alarm off to me of we need to see what's going on there. And in addition, down in Florida, also highlighting another county where those two intersect, where we have a high amount of people in construction or development going on and critical habitat. And the next slide. Just to wrap up my portion here, again, to bring us back to supporting those MSD goals, prioritizing that need for capital investment while we look for areas of enhancing our resilience and equity. The infrastructure sector, bringing that into our framework allows us to do that. Also alerts us to areas where we might see risk happening by combining different metrics and risk factors, overlaying with our different infrastructure systems that we can highlight and see where we might need to focus our attention. Also, again, on the very kind of simplistic level, just that quick visual analysis on our maps where we can overlay the different maps with these different combined risk metrics and see quickly where the issue of infrastructure system might interact with high risk. So kind of giving us the areas where life might be impacted further or these hot spots. Another highlight I would say is we have another dimension on those lines that we can provide the thickness of the line to give us some sort of dimension as to how important that infrastructure is. We use a color system in the energy infrastructure, and then we use kind of the thickness of the line in terms of the transportation with highways and waterways. A limitation that we currently have is that we can't include the information quantitatively right now into our combined impact value. So that multi-system metric, right now, we don't have the ability to kind of put infrastructure in there as a combined risk. We can only use it visually, but we're kind of trying to be creative and think of some ways we might be able to do that in the future. Something that we can do in the future is that we can always add more data as we see fit. Currently, we have in the works, and for at least a couple of states, we have data on Superfund or toxic sites. So we can use that type of information and look at how that's impacting our highest poverty areas or where there's high flood risks and how that intersects with some of these Superfund sites. I say we just have to be cautious there with how much data we want to add, right? We want to make the data meaningful and we don't want to make it too overwhelming on our maps. So that's why we kind of have a great team to kind of think together as what's most important to use. And that concludes my section. And I think I'll turn it back over to Horacio.